this computer. We are recording. Okay, so I just want to start off with a couple kind of administrative announcements about the lab specifically this week, and just maybe a couple comments about the lab too, things to watch out for. I'm grading lab 3 right now. That's the inclined plane one. Dr. Tech dropping the cart on the air track down an inclined plane, and some of the things I'm seeing, I just want you to make sure you're attentive to it on today's lab and tomorrow's lab for some of you. All right, so I'm sharing my Canvas screen with you. Yep, I can see the green border on it, so it looks like you've got it. The first point, I guess, is administratively where to find it. Here's your modules page. I did add one file to the midterm, which is my solutions to part A, if anybody finds that useful. That's sitting right there. All right, and then if you move, there's chapter 6 that we're in right now. Here's the material for today. There's 6.3, gravity and orbits, that we'll be talking about here shortly. And there's the 5th lab sitting right there. Okay, what you'll see, there's 2 documents for the lab handout. One is a PDF, just because it's a truer rendering of what I meant to type. The other is the Word document. Some people I notice like to download the Word document and paste their answers right into the Word document. Perfectly acceptable if that's what you want. Those 2 documents should be identical, but just the Word document's there for your convenience. You have to watch a video just to see the experiment, and one's called horizontal, one's called incline, and then rather than making you analyze the video, we're giving you a logger profile. It's the .cmbl extension on the file, and that has the data that is associated with the video you just watched. Okay, for the 2 cases, 2 different sets of apparatus, just a slight modification to the apparatus. One's horizontal, one's on an incline, obviously from the names. Okay, and so that's where you'll get your data. You do the analysis of it, but you also do a prediction. The prediction is to figure out what you expect the acceleration of the cart and the tension in the string pulling the cart to be. And for a reference, I would go to worksheet 5.4 when we did pulleys. Everybody did a problem where there was a mass on an incline or a mass on a horizontal plane with a pulley and then a dropping mass. In the horizontal case, I think on that one there was friction. You could ignore friction in this lab. You may find that if you have a difference between your prediction and your actual measurement from the data in the logger profile that we've given you, well, that may be the explanation, is you didn't include friction. So you just can't pretend friction doesn't exist, but I think you'll find it's a fairly small effect. All right, looking at one of these logger profiles, I just want to make sure you see and are attentive to what I'm seeing when I'm grading. And so I'm going to stop sharing that if I can find where Logger Pro where Zoom managed to put that. There it is, stop share. They move the toolbars around on me, and it's always fun. It's like a little game of hide and seek sometimes with the toolbars when you got multiple files open. So here's the logger profile you'll get for the horizontal case today. And what I see people doing when they're doing a fit, say on the top graph, is just coming all the way across here, every bit of data in it. And you need to pay attention a little bit to where did the motion actually start? Because if you look, I could do a fit on that. I mean, I could try to do a parabolic fit, and you can see the black line, hopefully, that will show up here in a second. It doesn't really match the data real well, does it? And that's because I'm using points where the object wasn't moving, where the cart wasn't moving. You can see the cart is pretty much at rest to almost a second is where it starts moving. That's the lag between hitting the collect button and letting the apparatus actually move. So ignore all this. And once you see that bracket right here, you can pull it. Okay, I can pull it. So I think right about there is where the motion starts. And I still don't have my black line matching my red line, which is my data. Once it gets to just a little over 2 seconds, that's about as far as the cart can go before it bangs on the far wall and bounces back. And so I really don't want to be looking at any of that data either. The action in the lab is taking place a little before 1 second to a little after 2 seconds. It happens pretty quick. Most physics experiments are over within a blink of an eye, literally one, just a little over a second. And now if you move to the correct spots, you'll notice the black line, which is the fit, and the red line, which is my data. That's Logger Pro gathering data every 1/30th of a second. So about 30 times a second is what I had it set to do. And now you got a pretty good fit. And from A, B, and C here, you can figure out what the acceleration of the cart would be. Okay. And so that's my one thing to point out. And that's same thing for the velocity. Okay. You'd see from over the first second or so, the cart was at rest. Ignore that part. Okay. We hadn't moved I had a little mass blocking the cart. I hadn't moved it yet. So again, just before 1 second to just a little after 2 seconds is where the action is. You can rescale this, by the way, and I think it's a handy thing to do. I just want to show you how. Why are we seeing negative numbers for velocity? And the answer is because when it hits the far end, it bounces back. And at the very end there, at about 2.3 to 2.2 to 2.5 seconds, I've got some bouncing. So just you can manually rescale it and make that be 0. Just clicked on the axis, and I can look, and it only goes up to about 2 meters per second. So I can manually rescale that. And you can see now it's more obvious to me that that's a linear curve right there. It's a straight line. Whereas on a different scale, it may not have been as obvious. Filling the graph data, um, filling the graph with the important data and that you can see is part of any laboratory science, I think, to highlight what we're looking for, which is this region right here, right? And the slope of that line, the velocity versus time curve, is the acceleration of the cart. And same thing for the force. Okay, notice it's pretty constant right through there. That's the tension in the string. And you don't need to be looking over here before the cart starts moving. And so you could average in that. The program will let you, but it would be incorrect because at this point, over at about half a second, the cart's at rest. At about 1 second, it's clearly moving. All you needed is data points right in there. Okay. And that'll get you the attention you need. Okay. So just a couple thoughts. I'm seeing a lot of people, like I said, including data over here. And then, that data has nothing to do with the motion that we're studying, whether that was tossing the ball up in the air on lab 2. It's the inclined plane data. I just want you to, not taking too many points off for that kind of thing. I'm pointing it out as I grade your lab. But if you notice your results aren't what you're expecting, that's often the reason, because you're looking at data that isn't germane to the motion that you're studying and that you're trying to predict. Any questions on that? Dr. Kim is very likely going to talk to those of you in his section this afternoon, point out the same things. Of course, if you're stuck on how to use Logger Pro, that's why Dr. Kim and I both stay around for couple hours during each lab while you go off and do it. That's certainly the time to pop back into the Zoom meeting and ask questions about how to do the analysis. As I saw, there were some people that just didn't seem to know how. Okay. Of course, if you wait till like the day before it's due, the afternoon it's due, something like that, you may not be able to get in touch with us to get help, but we're more than willing to show you things like this, let you see, share your screen with us, and, we'll give you hints on, hey, only look at this data right there. For my sections, use the same Zoom meeting that you used to come to class today. Dr. Kem, I don't know if he plans to send out a different Zoom meeting link for his people this afternoon. Just watch for an email from him, and hopefully he'll let you know. I'll see it too, so you can always come to me if he doesn't answer your emails. Questions about lab this week? All right, we'll make it due again next week like we've been doing. So you do have a week to work on it, but please don't wait to the last minute and expect help. That's never a good plan. All right, then we'll move on to today's material. I'll stop sharing that. Everybody's good for the lab. Enjoy it. Oh, by the way, if you have trouble doing the problems to predict what your tension and the acceleration are, the lab's a perfectly good time to get help with those problems. Just a kind of an aside on what you can expect on an exam. If we go through the trouble of creating a lab experiment for a particular physics problem, that means we think it's important. Okay. Projectile motion was an example on the last exam. These pulley problems like this, we built a lab with some variations in the apparatus because we think it's an important problem. If I was a guessing person on what might be on the next midterm, which is at the end of the month, a couple weeks from now, but still, well, you would say, they built a lab on these carts being pulled over pulleys by falling masses. They must think that's important. Maybe that's a question I should be able to do. And so, worksheets that map to lab experiments, I think take greater weight in what you should be looking at to prepare for an exam. And, there's only 10 lab experiments we do. Each and every one of them is there for a reason, okay? Because we think that's an important physics concept for you to take away from the course. All right, anyway, that's just a little hint, I guess. Let me put some of this stuff away on my screen so I don't have to play with it and have it be tripping over it here. I'm going to switch over then to my PowerPoint. Why is it? Okay, don't save. Switch over to PowerPoint because we got, of course, like we always do, a couple polling questions just for today. Unless anybody has any questions, I think Newton's universal law of gravitation is a profound law in the sense that if you come back second semester, you're going to see that a similar law, not between masses for the force of attraction between masses, but for the force of attraction between charges is going to come before you. And you'll see that it looks very similar in form to Newton's universal law of gravitation. And if you happen to study Coulomb's law in high school, perhaps you'll know exactly what I'm talking about. In fact, there was a great emphasis in physics wondering if all these forces that we have that take place over a distance, like gravitation, the moon and the earth don't need to have any connecting objects between them in order for them to exert forces on each other. Similarly, charges don't have to have any contact between them, and yet they exert forces on each other. Magnets don't need to touch, and yet they can push and pull on each other. We call these action at a distance forces, and we notice there's a similarity in the form by which you calculate these forces. And so Newton's universal law of gravitation is the first such thing that you see that looks like that. And at the end of the day, it's an equation, right? It is just an equation. Now I'm looking here, put that away. Don't need that. Where is PowerPoint? I don't see a green border around it, so I'm going to stop sharing it and try again just to make sure you can see it. There, now I see a green border, and hopefully you see the very first slide. And just a quick review. I think that slide right there tells you pretty much all we need to know about Newton's universal law of gravitation. It is the force of gravity, what we've been calling weight up to this point. It is mass times an acceleration due to gravity. And Newton said it's equal to a constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Okay, times the product of two masses, the two things that are attracting each other, divided by the distance between their centers squared. And if you divide away the mass, you can find that the acceleration due to gravity anywhere is just that constant times whatever the mass of the thing that is creating an acceleration due to gravity, the planet, Earth, whatever it is, again, divided by the distance between their centers squared. And so if you want to get 9.8 out of that, you put in the right constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. You look up the mass of the Earth, you put that in for mass of the planet, you divide through by the radius of the Earth and you square it, and sure enough, out pops 9.8 meters per second squared. And 30, you'll get a chance to do that here in a moment on the worksheet. That's kind of it. It is an equation, but it is an important equation because what is the reason the moon goes around the earth or the earth goes around the sun? That gravitational force right there is the only force acting on either the moon as it goes around the earth or the earth as it goes around the sun. It must be the net force. It must be what is supplying the centripetal force. Okay. There is no force in our catalog called centripetal force, but gravity fills that bill for us. And since it is the only force acting on either the moon in its revolution or the Earth in its revolution around its central body, the sun, Earth or the sun, in the case of Moon or Earth, it must be equal to the mass times the centripetal acceleration, the velocity squared over r. And that's an important point because that allows us to figure out how fast things are going in orbit. All right, and so that's the bottom line. It is an equation, and you just use the equations we've had before in the class to calculate centripetal accelerations, velocities, speeds of things going around in circular motion. Heck, you can even, once you get a acceleration due to gravity someplace, you can figure out how long something might take to fall, or what kind of projectile path it'll go through as a result of that. Because this equation allows you to figure out g anywhere. You can figure out the acceleration due to gravity on Pluto if you want. All you have to do is know the mass of Pluto and the radius of Pluto, and you got it. And that's the meaning of the word universal. The belief is that this constant capital G, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, the belief is that that's not just something local here to our solar system. We believe that was something that came into our universe at the time of the Big Bang. We don't know why, but it is a constant that we believe is everywhere in the universe that has come into being since the Big Bang in the 14 billion years or whatever it is since that time. All right, so a couple polling questions then with that as an introduction. Here's if I can find where, yeah, there it is. It's up now, polling, and I got to get to the right one. And get a second to read that, I guess. Hopefully that's the same one. And this was discussed, I guess, in our little pre-lecture video last night. Why doesn't the moon fall into the Earth? It's an interesting question. They're gravitationally attracted. Why doesn't the moon just crush right into the Earth? All right. It's an interesting theory that some of you have. Not the one I would tell you is the correct one, but a number of people have it. Five more people. Got 20 folks in right now. Here's your clue right here. This was in last night's video. Shoot a ball horizontally off a mountain. It's kind of got the answer in it right there. All right, I'm going to end it here. We're still waiting on three people, but we've been well over a minute now. Got to move on to other things. The answer is D, right? As this little picture right here tells us. Let me make it a little bigger for you. Okay. If you look, first, not enough speed, it hits the ground someplace. Projectile motion path, parabolic. But if it's enough speed being launched, it is able to fall the entire time, but the ball falls at exactly the same rate as the Earth's surface curves away, and so it's never able to hit the ground. The International Space Station is constantly falling towards the Earth. The moon is constantly falling towards the Earth. That's the nature of an orbit. The good news is it doesn't fall fast enough. It falls at a rate such that the Earth's surface curves away and it just continues to fall as it moves around. And that's why people in the International Space Station are weightless. Okay, relative to the space station, which is falling, somebody inside the space station falls at the exact same rate. The space station isn't able to exert a normal force on anybody inside of it. And so, relative to the walls and the floor of the space station, they just float around because they're all falling at exactly the same rate. And that's why you see it. Yeah, there is an effect of sun and other planets, but that's not what keeps the moon from hitting the Earth. And by the way, there is always this notion with black holes. And if you've been paying attention to the news, you saw the Nobel Prize in Physics was awarded this week for the study of black holes. Roger Penrose is the famous scientist that I recognized on the list. The others I didn't know. And there's always this fear that somehow we'll get sucked into a black hole. Well, a black hole is just a very massive object, huge mass, huge force of gravity. In fact, a black hole is black because it is so massive that nothing can escape its gravitational pull. And here's the odd part, even light. Okay, and so light can't escape from a black hole. There's a huge mass there. We just can't see it because we see light and light can't escape. And so what I guess what we find here is, can you be sucked into a black hole? And I suppose there is some small mathematical possibility if you're at rest right outside the black hole. But currently at the center of our solar system, there are about a half a dozen stars that are actually going in an orbit around, I said solar system, at the center of our galaxy, the Milky Way galaxy. There are about 6 or 7 stars that are rotating, revolving, going in orbits around this thing that we can't see at the center of our galaxy, which we believe to be a black hole. None of these stars are being sucked in to the black hole. They just go around in orbits, exactly like the moon goes around the earth or the earth goes around the sun. And so that's, unless you just happen to be at rest, you'll never get sucked into a black hole. You'll just be orbited. Now, you could get so close that your orbit is in that what's called an event horizon for a black hole, in which case you're like the light. You'll never be able to escape it, but you're not really being sucked into it. You're just orbiting it. And that's what happens because the black hole has size. And as you fall into it, you'll fall as its curvature curves away and you'll just wind up in an orbit. That's how it works. So the 5 of you that went with D, good work. That is the right answer. All right, let's get to the right slide here. Oh, come on, PowerPoint, don't do it again. I hate that little little wheel that curves around here. That's always a bad sign for me. So we'll stop sharing. We'll put PowerPoint away, and then we'll reopen it. And then we'll be able to start up again. And it's going to ask me if I want to send messages to the home office at Microsoft, and I don't. But we're going to have to put up with that too. Gravity and orbits. Come on, PowerPoint, you can do it. All right, there's the one we just did. And I'll share it with you again if I can find out where Zoom decided to put my toolbar. There it is, share screen one more time. Why? All right. All right, hopefully you can see that. We're going to make that a little smaller, make it so that, make the side piece here, and we'll stop sharing and move on to the next one. And launch it. Go ahead. And so suppose we had no atmosphere. Top of Mount Everest. What acceleration? All right, I'm happy to see them. No, I don't need to send a message to the home office, Microsoft. All right, looks like 20 people are in. 20 people played 21. There we go. And I can almost live with 2 answers here. And we'll talk about why here in a second. All right, we got 23 to 25, over a minute, almost a minute and a half here. We're going to stop. And I'll share the results with you. And I want to remind you, I guess, that we said that G will be the free fall acceleration. This thing is falling, always falling, always falling, always falling towards the center of the earth. It appears to be the y-axis locally, right? The vertical direction locally. But as you move around a spherical object, that becomes more of a radial direction, always falling, right? That's the deal with G. Now, right near the surface of the earth, that value is 9.8 meters per second squared. And that has to be equal to the centripetal acceleration, right? There are no other forces other than gravity. If you like, put an m in front. So the weight is equal to mv squared over all, and then immediately cancel them out. And so this tells us one of the equations that we were working with yesterday, actually not yesterday, in the pre-lecture video, v squared is equal to g times r, right? And so what causes the Earth to circle, or the satellite here to circle around the Earth, is the acceleration due to gravity. And so I think the best answer is approximately g. Now, for those of you that went with A, if this is what you were thinking, if you were thinking, well, g is the value right there at the surface of the Earth, up here where this orbit is, g is going to be a little less. Okay, that's supposed to be a G, not a Q, is a little less than G at the surface. And that's why you picked A. Well, then I can live with your answer, because you're right. G would be a little less, right? We said that G, the acceleration due to gravity, according to Newton's universal law of gravitation, would be that constant, G, times, in this case, the mass of the Earth, divided by the radius squared. And up where the satellite is, well, there's the radius of the Earth, right? Usually capitalized. And out at the orbit, there's a bigger value out to r, and I went a little too far there, but since this is a bigger value, g would be a little less. And so I can live with A if that's the reason you picked A, okay? Yeah, it's free falling, so it's g, but it's the local value of g, whatever it is where the satellite happens to be, whatever distance from the center of the Earth it is. All right, so good on that one. I think the majority of people got it exactly what I would have said is the best answer, but 9 other people went with something that, if you had the argument in your mind that I just went through, I'm fine with your logic. Stop sharing that. We'll move on to the next one. And I'll move to the next slide, I guess, if I can get it. Yep, there we go. And I'll launch it. Yeah. Like, what? All right. We added a person. Welcome, whoever you are, number 26. And I'm going to end the poll here and share the results with you. And don't you hate none of the above questions? But I think this one is right. The first one is just to make sure everybody has this. G, the acceleration due to gravity, 9.8 meters per second squared at the surface of the Earth, is not the same as the constant in Newton's universal law of gravitation. And if you're the person that interchanges upper and lowercase letters in physics, you might want to change that, because obviously that'll confuse you. Much like I had to kind of chuckle at the tension versus period also aren't equal. One's a tension vector, the other is a period of interval of time, a delta t. And that's why they both have the same letter. You just got to see context, right? We have that in the English language regularly, right? Where two words sound exactly the same, might even be spelled the same, and have completely different meanings based on context. And same in physics. And that's just part of learning the language of physics, I guess. In any event, that's the point of number one. The word universal means it doesn't have a different value at various locations throughout the universe. We think it's the same. We could be wrong. Right? We've never been beyond the moon, so we could be wrong, but we do believe that at least on the moon and the earth, the two places mankind has been to in the universe, the value of G is the same. And next week's lab, you'll get a chance to see that. Okay, you'll actually predict and then measure from some footage that some of the astronauts from the Apollo missions did. You'll be able to, somebody will drop something, you'll be able to measure from that video what the acceleration due to gravity on the moon is. Based on our understanding of the mass of the moon and the radius of the moon, it's exactly what's predicted from Newton's universal law of gravitation. And so that's the subject of next week's lab. We'll wet your whistle on that. Could you determine it? The word that makes C false is the word directly, right? Because if you measured the free fall acceleration by dropping an object, okay, you could get G, but you would need to know the mass of whatever it was, wherever you were standing, Earth, moon, wherever it is, and you would need to know the radius of those two things, of that thing, whether it was the Earth or the moon. So you're not making a direct measurement because you need to know both of those. If it had dropped the word directly, you might have been able to say C is possible, but C is only possible if you know what the mass and the radius of wherever you're standing and measuring the free fall acceleration is. By the way, this brings up a point about gravity. People use gravity as a noun, and it is in some sense, but in a physics sense, it's usually an adjective. We talk about gravitational acceleration or the acceleration due to gravity, right? It's the modifier of the acceleration. Or we talk about the force of gravity, the weight, the gravitational force. So be careful about talking about, well, what causes that? Gravity. Okay, the acceleration due to gravity, the gravitational force. I'll tell you this. When we start talking about energy, we'll talk about gravitational energy. Again, it becomes an adjective, a modifier on the noun that is either the property we're looking at, acceleration or force. And I hear people talk imprecisely, force of gravity, acceleration of gravity, okay, as opposed to gravity being just a thing itself. It is, but what aspect of the gravity are we talking about? All right, one more, and we'll move on here. This one actually comes from the MCATs. And this one, you almost have to do a little bit of math, maybe on a scratch piece of paper at wherever you're watching this, or wherever you're participating from. And so you got three different planets or moons or whatever they are, and you got a mass of a 60-kilogram person. Which place is his or her weight the greatest? And M is, of course, the mass of the planet. And you can see the planet masses are getting bigger, but so are the radiuses. Radii. And I'll give you a hint. This first day with Newton's universal law of gravitation. We'll call that the planet. Mass of the person, I'll leave unsubscripted like it was over there, divided by r squared. That's the hint. Most of you are seeing it though. All right, 23 or 26, you're in. 3 more people. Cut it off here in a second. Most of you have it though. 18 people. You guys nailed it. Good job. I'll just share it with you. Yeah, and the question, I guess, is which thing has the greater effect? The mass being tripled or the radius also being tripled? And you can see because of that 3 right there, and that squared, it's 1/9, right? So although the mass takes you up by a factor of 3 due to the mass, The radius here takes you down by a factor of 1/9. Same thing here, mass goes up by a factor of 2, okay? And the radius takes you down by a factor of 4, okay? And so that leaves, I guess, this guy here is the biggest, because both of these, B and C, that radius taking you down by such a big factor, greater than the factor the mass took you up, makes A the correct answer, and that's why you guys are right. So that's it. There's the answer in more detail if you want, but you can see what I just talked about, the 3/9 factor for choice C, the 2/4 choice for B, and then 1-to-1 for A. And so 1 is greater than a half is greater than a third, and that's why A is the right answer. And that's why it's on the MCATs. I have no idea what that has to do with being a doctor. Maybe it's just logic skills. All right, any questions on anything we've done today? All right, last thing I guess I got is a quick problem on the worksheet. And so I'll stop sharing these. 3 groups again, 3 problems. Share my screen. I'm gonna, let's see, where is, all right, Acrobat, there it is, Acrobat. Just a few words up at the top with the numbers, so you don't have to go scramble into a textbook or Google to look them up. There's Newton's universal law of gravitation. One group is going to be figuring out what the mass of the Earth is based on the fact that G is 9.8. There's all the digits if you want, 6 digits to figure it out. Another group is going to look and see, okay, what is the acceleration due to gravity up at the top of this mountain, where that's the radius. And then the third group is going to take a trip out to Mars and figure out what the acceleration due to gravity is on Mars. Using the same thing. So that's our plan. Shouldn't take you much more than 5-10 minutes. We'll call you back. We'll check some numbers. And where's my hopefully that's resolved. Let's see. So I'm going to go to breakout rooms, 9 rooms here, and create. And so problem 1, Maddie, Megan, Michael in room 1. Also doing problem 1, Kristen, Kyle, Olivia in room 2. Chenyi, Katie, and Ya, you're in room 3. All of you are doing problem 1. Okay. In room 4, Cora, Nina, Sydney doing problem 2. Allison, Anna, Tommy in room 5 doing problem 2. Andrea, Jackie, and Rachel in room 6 doing problem 2. Everybody else, you're doing problem 3. Room 7 is Ellen, Emma, Shanice. Room 8, Elena and Stephanie, and room 9, Aiden and Eberici. So you're the last people there, you're doing problem 3 out on Mars. Hey, see you in about 5-10 minutes. All right, any questions on how to get this set up? Understand what you're doing? This really is just put the numbers into the equation. It's what everybody wants for a physics problem. G, mass of the Earth, divided by the radius of the Earth, put that in for R squared. See what number you get is. Well, hold it. Other way around, solve for mass of the Earth based on those numbers. Okay? Good to go? Any questions? All right, have fun. When you got a number, you can actually Google it and see if you're right. So you'll know if you got the right answer. Moving on.
Wait, I think we're problem 1.
Oh,
Yeah.
you said that. We'll start using these numbers, estimate the mass of Earth, assuming approximate spherical symmetry. Average Earth radius is 6.371. 6.371,009
Mm-hmm. Yep.
times 10 to the 6th. And
Yep.
then the mass.
That's what you got to find.
Yeah, we have to solve for the mass so we can use that equation that he gave us.
Just so that we said this is the equation. I'll help you out with that. Over, in this case, it'll be radius of the Earth squared, right?
Mm-hmm.
And you're trying to find that. And so this guy will go right there, right?
Mm-hmm.
And G will go right there. And constant capital G will go right there. Solve for mass of the Earth. Not too bad, huh?
No.
Oh.
Yeah. You know 3 of the 4 things, solve for the 4th. I'll leave you guys alone.
Thank you.
All right. Thank you.
You bet. All right, leave the room.
So lowercase.
Hi, I accidentally left the Zoom session by accident.
Okay. What do you remember what room you were supposed to be in?
Yeah, I was in room 7. I'm sorry.
No problem. It happened. It's internet. You saw what PowerPoint did to me. I think I just moved you there, so you should be moving there shortly.
Awesome. Thank you.
You bet. All right. All right. Any questions from you, you three? Here's what I think you're doing. Here's your equation, right? G is equal to that's your equation. I think you know 3 of the 4 things. The only thing you don't know is mass of the Earth. So solve for it. And then you can always check your number by going to Google to see mass of the Earth is well known. So you should be able to check it. All right. But the problem gives you, or at least the worksheet gives you those 3 numbers. Plug them in, solve for the mass of the Earth. Good to go?
Thank you.
All right.
Yeah.
Not a bad problem. This one's one of the easier ones, I guess. I'll leave here. All right. All right, I got a request for help from another room, so I'll any questions on what you all are doing?
Yeah, we're kind of stuck just even with where to start for number
Okay.
2. because it
Here's what
doesn't
I would
really-
do. Let me give you my whiteboard here. And there's a couple of ways you can do it, but bottom line is you're working with this equation, right? And now the radius that you're going to put in there, that's at the top of the mountain, okay? So 2 approaches, you know what the radius, you know what G is, right? You can almost look at problem 1 and try to figure out what the mass of the Earth is. And then once you got the mass of the Earth, increase your radius. There's a kind of a clever math way you can work around that though. Okay, so you can go sea level. And which way do I want to do it? Let's go the other way. Let's get rid of that. At top of the mountain, which is, I can't even pronounce that, Chimborazo, I guess. So I'm going to just go mountain because I can't say that. Wouldn't that be G, mass of the earth, divided by the radius at the mountain, at the top of the mountain, squared, divided by G, mass of the earth, radius of the earth at sea level, squared. And wouldn't those two cancel? And so you don't even need to know them. All you need to know are the radius at the top of the mountain, the radius at sea level, and G at sea level. And you could figure out what G is at the top of the mountain. It'll be a little different.
Would G at sea level just be like your standard
9.8. Yeah.
Okay.
In fact, it's at the top of the worksheet. It's 6 digits at the top of the worksheet. But yeah, 9.8 is what you're putting in right there, meters per second squared.
Perfect.
Okay. See how clever that's a clever math trick. You could always do a little more brute force on it, figure out what the mass of the earth is from G at sea level, and then plug back into this equation as well. That just takes a little more calculator manipulations. All right. I'll leave you guys alone. Question from 7. Sorry, I was working with I was in group 4. I'm doing better at getting around today. What can I do for y'all?
Yeah, we were kind of confused about how we were supposed to find the gravity of Mars without
Okay.
using like the specific Earth values.
Yeah.
So would we just
I can
put-
show you that. There's a little bit of a trick, I guess, right? Okay. And so let's see. Acceleration due to gravity is G, in this case, mass of Mars, right?
Mhm.
Divided by radius of Mars squared. All right, so let's see, that would be G. Now, what do we know about the mass of Mars? 0.107 mass of Earth.
Yes.
And this is kind of a slick trick, but these are the kinds of things that make your life easier if you can learn to do them. And now the radius is 0.532 radius of Earth, and all of that is squared. So one way to do it, I guess, just brute force, look up G, look up the mass of the Earth. It's in the back cover of your textbook. Look up the radius of the Earth and just plug all those numbers in, right?
Mhm.
You could do it that way, and nothing would be wrong if you did it that way. Here's another way, though. G, mass of the Earth, radius of the Earth squared, times all those numbers right there. That's 0.107 and 0.532 squared. Those can come out. What's this? Isn't that just 9.8? Make sense? It's kind of clever, isn't it?
Okay.
So all I got to do is take a number I know, 9.8 meters per second squared, multiplied by the factor for mass, multiplied by the factor for radius, remember to square it, okay? And that should be able to, I can correct what the radius of the Earth is. As I said, if you want to just look up the numbers, mass of the Earth, radius of the Earth, and capital G, that's another way to do the problem as well. All right. Hey, I think I got to call everybody back. We're just about done with time here. So I'm going to leave and stop sharing my screen. And I'm going to leave the room and I'm going to and right, everybody's coming back here. I mean, we're still only 24. All right, well, we're just about done with time here. I did get to about 5 of the 9 breakout rooms to talk, hopefully gave you some hints. In many cases, there's 2 different ways to solve the problem. I showed some of the groups some clever ways, some shortcuts to do less calculator manipulations. But let's say you're doing problem 2 and you don't know what the mass of the Earth is in order to get that value of G. Well, it's in the back cover of your book. Or you can do problem 1, because problem 1, they've calculated the mass of the Earth from Newton's universal law of gravitation and use it to get what you're asking to solve. All this astronomical data is on a table in the back cover of your textbook. But Google knows all these answers too. If you Google what's the mass of the Earth, it'll tell you what it is in kilograms for problem 2. But there is a clever way to do the problem without knowing the mass of the Earth. And I showed that to a couple of groups. Same thing for the Mars people. You could go and Google what the mass of the Earth and the radius of the Earth is, or go to the back cover of your textbook and actually calculate then from the information given what the mass of Mars and what the radius of Mars is, and then just plug it into the acceleration due to gravity equation. That's one way. But there was I showed at least one group, a shortcut on that. If you just know that the acceleration due to gravity on Earth is 9.8 meters per second squared, you could correct that number based on the Mars values without ever having to look up those numbers. Choice is yours. One's a little bit of a shortcut. The other is more of a brute force method, but in both cases, you'll get to the same result. That's all I got, I guess. Any questions on anything? Okay, so what you have to do, I think most groups were close to finishing up their problem. Wrap it up and upload your solution to Canvas by, today's Wednesday, by Friday. I'll be hanging around here for office hours at 9:30. And then as normal, I'll be back at 10:30 as well for a second round for people who have to go off to class right now, if you have any questions. And don't forget, homework is due tonight, right? For mastering. There is a homework assignment due at midnight tonight. And some of you will see in lab tomorrow, and you guys have a great rest of your week. Any questions? All right. Have a good day.
Good question. Sorry.
I'm going to stop